Okay, so this is Monday, January 5th, and here in balmy Minnesota, it's -9 degrees in Morristown. Yes, because we're hardy Minnesotans who are still here. Balmy means like wonderful. And in my classroom, it is almost 60 degrees. Previous to now, it was less than that. And so we are hardy and we are doing our Minnesota thing. Oh, and I was requested to give a joke, so the only joke I can give is my favorite joke. What did the 0 say to the 8? Nice belt! I love it every time. Okay, so I had a note to myself that January 5th I was going to do number 3, and then I was going to add to close secant and secant. Oh, yes, every once in a while that little flash will come up. I don't know how to get rid of it. If you remember before break, I had put a cosecant graph on there for the people who are going to be gone, just so that they would kind of have an idea of that. So really we're graphing cotangent to cotangent x over 3. So what's going to happen here is it's going to change some points that we're plotting. If you remember, cotangent does not have an amplitude. Likewise, tangent doesn't have an amplitude. They go to positive and negative infinity. The period of tangent and cotangent is pi, so this is going to change the period as well. And but that too we'll just have to remember. If I forget it, someone will, I think, probably remind me. And so this is like 1/3 x, so b is 1/3. The period of a regular tangent or cotangent is just pi. So this is pi divided by 1/3, or 3 pi. So our period is 3 pi. When I'm going to graph the cotangent function, I could maybe find a piece of graph paper. And if you remember back before Christmas, we looked at where kind of the period would begin and end. Since there's nothing added or subtracted here, the period begins when x over 3 is equivalent to 0, and it ends when x over 3 is equivalent to pi. And that one will just give us our 3 pi. This will give us x equals 0. This will give us x equals 3 pi by multiplying each side by 3. Now, for cotangent, that's where asymptotes are. So these are our asymptotes are at our beginning and our end. So at x equals 0 and x equals 3 pi, there are asymptotes. And I'm going to go every 3 boxes. I think I feel like I have to go by a little different. Actually, I'm just going to go 1, 2, 3, 4 boxes, and I'm going to make that pi. 1, 2, 3, 4 boxes, and I'm going to make that 2 pi. And then 1, 2, 3, 4 boxes, and I'm going to make that 3 pi. I'm a little spread out there, but that'll help me as I plot some points. So we just said that our asymptotes are at x equals 0 and x equals 3 pi, and that's going to be for one period. So I have to just move something a second, I think. Okay, so I'll put in that asymptote there, another asymptote here. If I went back to negative 3 pi, it would be right there. I'll maybe even put those points on there as well. And slide this asymptote just a little bit to the side. Okay, so I can get 2 full periods in here. There's my asymptotes. When I plot some points, since this is 2 times cotangent, ordinarily I'd want to find when that is equal to 1. Those kind of old maximum and minimum values are easiest to plot. For sine and cosine, and they are for cotangent and tangent as well. But in this case, because it's 2, I have to remember that that's going to make things go more quickly as it goes up. So I'll go to 2 there. That'll kind of remind me when I'm plotting points that I have to do that. Okay, and I don't even know what to do when that happens. So it will just happen. All right, so then I have my asymptotes. Then I want to plot some key points. When I plot points, for cotangent, I'm just gonna, I don't remember if we exactly talked about this, but for cotangent, between the 2 asymptotes, halfway is a 0. Between the 2 asymptotes, and then halfway between the asymptote and the 0 is a maximum, and then halfway between the 0 and the end asymptote is a minimum, and then it's kind of looks like that. And that's going to be my cotangent function. So first I'll find that middle. If this is 0 and 3 pi, half of 3 pi is 3 pi over 2, so that's 1.5 pi. So right there, I'm going to have 0. And so my 0 is at 3 pi divided by 2. So halfway between the 2 asymptotes. And I'll maybe write that halfway between the 2 asymptotes. And then to find my other 2 points, I'm going to go halfway between the asymptote at 0 and this value of 0 at 3 pi over 2. And that would be, half of that is, we'll say it's kind of a, maybe max is a bad word because it's not a, it's just a point. A point to plot will be 3 over 2, or 3 pi over 2 times 1/2, so 3 pi over 4. And that point will be at what would ordinarily be my maximum of 1, but in this case, it'll be 2. So at 3 pi over 4, 1, 2, 3, it'll be 2. So, and I can do the kind of the image over here too. There's negative 1.5, and then halfway between here and here, 1, 2, 3, 4. It'll be at 2 when I put that one on there. Then halfway between these 2 at my 0 value, which is 3 pi over 2, and the end of my period at 3 pi, one way I can find that one is just find the average of those 2. So I'm going to take 3 pi over 2 plus 3 pi and divide that by 2. And so I'm going to convert that into 6 pi over 2. So 3 pi over 2 plus 6 pi over 2 all over 2. That's 9 pi over 2. All over 2, when I invert and multiply, it'll be at 9 pi over 4. And then comma 0, or excuse me, I keep wanting to say 0. But that'll be at a point to plot that would ordinarily be -1, but now it's going to be -2. And 9 pi over 4 is what? 2 1/4. Is that right? 2 1/4. So 2 1/4, I'm at my -2. And so from here, you know, and I could have just counted boxes 1, 2, 3, 4, 5, 6, and just go 3 of those. But I want you to mathematically kind of know how to do that as well, so that if it doesn't work out to be something that's easy to count, you can still figure it out. So then the black curve is going to be the answer there. And that's the best I'm going to sketch that in. And so that is the graph of y equals 2 cotangent x over 3. Any questions? And I have some slides that follow that tell a little bit about, plotting some points. There's the graph by the book authors. We graphed the first 2 periods that are shown on here, not the third one. And then I wanted to graph y equals secant x. Oh, very, no, okay, I'm back on track. For those of you who are listening to this possibly, I just paused for a minute and I'm back now. So, and there's that sign that just always comes up. And the one time I tampered with it, things didn't go well. So I just close it every time. I wanted to just take a few minutes and graph y equals secant x before I go on to like more complicated secant and cosecant functions. Just a reminder, secant and cosecant have asymptotes when their respective cofunction sine and cosine are zeros. They have asymptotes, and they have kind of a relative maximum or a relative minimum where the opposite happens in sine and cosine. So where sine has a relative maximum, the cosecant will have a relative minimum. And so we can kind of graph it. I thought starting with a graph of just looking at secant, if you remember before break, we did a graph of cosecant. So when you're graphing these inverse functions, my hint to you would be always graph the original sine function first, and or cosine function. So first, we're going to graph y equals secant 1 over cosine x. So we're going to start by graphing, or excuse me, that is y equals cosine x. So first, we're going to graph y equals cosine x. And that's a pretty easy function for us to graph. I'll just go 1 pi and 2 pi. And I'll go back a period to 1, 2, 3, 4, negative pi. And those are at 1 and negative 1. When I graph a plain old cosine, if you remember, I'll put this one in red. It starts at its maximum, the middle, the minimum, the middle, the maximum, and then we can kind of backtrack the middle, the minimum, the middle, and the maximum. And then we can kind of just draw in that cosine curve. So that's our kind of first graph. Then when we graph the function that we're going to be using here, we're going to graph y equals secant x. We want to remind ourselves of a few things. So it'll have asymptotes where cosine is equal to 0. So asymptotes will be, and I'll go for one period, but then I'll backtrack. So one of those is going to be at pi over 2. Another one is at 3 pi over 2. A previous one is at negative pi over 2. And a previous one to that is negative 3 pi over 2. So if you look at that, you'll notice that the asymptotes are happening starting at pi over 2, and then they go by pi. Because if I take 1 pi over 2 and I add a whole pi, which would be 2 pi over 2, I'd get to 3 pi over 2. So our asymptotes are at x equals pi over 2 plus pi x. So that's the way that I can determine where all of my asymptotes are going to be. And so then I'll just draw in some asymptotes for this graph. And I'll draw them in this purple color. And wherever there's a 0 for cosine, there's an asymptote for secant. So there's my asymptotes. The other things I want to be able to plot here are those kind of top relative maximum and minimums, and they correspond to the actual maximums and minimums here, but they're the opposite. So where the cosine of x is equal to +1 here, the secant, and that's a maximum, the secant is going to also equal +1, but that will be a minimum of that. And so maybe I'll graph this in yellow. I'll put an X there. Each of those minimum or maximums still have a value for secant, but then I'll start with this one. Then the graph has kind of that, it's really not a parabola, but it kind of has the view of a parabola. And then since I didn't draw out further past 2 pi, I'll just kind of make it look like that. So if we can find those maximums or minimums for sine or cosine, then we can graph the secant and also the cosecant. So the yellow graph is y equals the secant of x. Any questions on that? I thought it was a good idea to kind of just go through the actual graphing of those two so that you could kind of see that. And then someplace here, here's a slide that just kind of tells you that. My feeling is that if I just show you that slide right away, then you don't really get a sense of how you're going to actually physically accomplish this. So we had done this cosecant before break. If you look at the light gray, and so I'm looking at this graph right now. If you look at the light gray, that was the sine of x, and then wherever the sine was equal to 0, there's asymptotes. And so as usual, our book authors, they just don't draw in that asymptote that goes at the axis there. Visually, we don't see that from them. And then every pi where sine is equal to 0. So the period is 2 pi. The domain is all x that are real numbers except when x equals n times pi. And the range is from -infinity to -1. So there's y values up to -1, and then from 1 to +infinity. Notice the -1 and +1 are included. And the vertical asymptotes there are x equals n pi. And the origin is where it's symmetric with respect to the origin. So if you rotate cosecant 180 degrees, it'll match on itself. And then the one we just did is right here. So if you want to, add to that the period again, and then the domain. Here, it's just that offset because cosine has zeros at pi/2 and then repetitively at intervals of pi. And it is symmetric with respect to the y-axis, so it can fold in half. Does anybody need to see this anymore? Okay. So then this just kind of gives a little bit of information. We just kind of looked at this. I'm not going to read through that. You can read about the hills and the valleys. And the x-intercepts become vertical asymptotes. We've kind of talked about that. Now we want to sketch something like the graph of y equals 2 cosecant x plus pi/4. So my hint or my message to you is that we're going to graph first y equals 2. Instead of cosecant, we're going to graph the 2 sine of x plus pi/4. So, we've been on this break. This is an excellent review of even graphing kind of something with regard to sine. So for this part, the amplitude is equal to 2, right? because it's that value that's right here. The period is still 2 pi because b equals 1. So the period is 2 pi. It is horizontally shifted, and we're going to address that by saying where it starts and stops. It starts when x plus pi over 4 equals 0, and it stops when x plus pi over 4 equals 2 pi. 0 and 2 pi being the beginning and the end of the periods as we go. So then I have to kind of solve those. So at x equals negative pi over 4, and this one is the same as x plus pi over 4 equals 8 pi over 4. So when I subtract 1, x equals 7 pi over 4. So if I want to just graph the plain old sine, I've got an amplitude of 2, a period of 2 pi. I know where a period starts and ends, and I can kind of just graph that part and then graph the cosecant by looking for where my asymptotes are and what happens there. Maybe I'll work on that later. Oh, thank you. I just got some advice on that. Okay, I will pause a moment next time it comes up, and then maybe I can take care of that. Who knows? We'll see. I know that I don't push it because one time I pushed something and then things went bad for me. So I am a little hesitant, but all right. So now I'm going to graph this one, and I'm going to put some scale on here. I went with 4 boxes to equal pi. And back 4. So I'm graphing this 2 sine x plus pi over 4. I know my period starts now at negative pi over 4, so it's shifted to the left pi over 4. And so at the shifted value, I'm going to be 0. And then if I kind of just count 2 boxes ahead, I'll be at my maximum. And I didn't put that scale on there. 1, 2, -1, -2. So I'll be right here at 2. And then 2 more down the line, I'll be back at my middle. And then, oops, 2 more down, I'll be at my minimum. And then 2 more, I'll be back at the middle. So then I can plot these points as well, and then I'll get kind of a decent curve there. And if I wanted to go back 2 more, I'd be kind of at the middle there. Makes it easier for me. Then I'll have 2 nice periods. So here's my sine function, and now I'm going to do the reciprocal function. So I'll do that. Now I'll graph y equals 2 cosecant x plus pi over 4. So then for this one, I want to look at where my asymptotes are. And they are where the function that's currently graphed are equal to 0. So I'm going to start with I've got negative pi over 4, and then I've got, it looks like 3 pi over 4. And then it looks like, what would that be for? 7 pi over 4. And so if I count, these are going up by pi again. So, let's look at this. Keep current color scheme. And is that a good one? Okay. All right, we'll see how that goes, because I don't think that's the one I picked when I screwed everything up. But x equals, we can say that it's at 3 pi over 4 plus pi n. Is the right letter there. And so now I'll put in my asymptotes. And again, when I'm doing this, it's pretty straightforward that my asymptotes are where that function is equal to 0. Oops. And so when I'm testing you on this, which will be between now and the end of the semester, this is my expectation, and I'll probably even have questions about that. What would you graph first if you had to graph this 2 cosecant? And your answer would be that you would graph this one first. And then, you know, I'll probably say graph that one and then use that graph to graph the solution. I'll put this solution in blue. And again, I'm not going to do a lot more work because we just went through that other one. Here, I'm going to have zeros, or excuse me, those relative maximums and minimums, and then I just draw my kind of little bowls in between those two asymptotes every time. And that's what it looks like. For this one, if we consider the sine function, which we'll want to kind of know about as we go, the amplitude is 2, the period was still 2 pi, so it didn't change, and it had a horizontal shift of pi over 4 to the left. So this is a great review of the earlier part of the section, and then doing these reciprocal ones as well. Now, I also have, here's that one, and here's the book author's picture of this, very comparable to what we had. The next one, oh, maybe I have that on here. The next one that I'd like to do is just briefly y equals the secant of 2x. And this one, the period is different, correct? And so for this one, I'm going to start with y equals the cosine of 2x. The amplitude here is 1. There's no horizontal shifting, but our period is 2 pi divided by 2, which is b, and so the period of this one is just at pi. And so this is a pretty straightforward graph as we look at that. Oops. And I'll just go over to pi, and I think those intervals. And I'll put 1 and -1 on here as well. If I graph the cosine, I'll graph that in red. The cosine of 2x. So the period is at pi. It starts at its maximum and then goes to the middle, minimum, middle, maximum. So I'll just back up middle, minimum, middle, oops, maximum. And so here's my original that I'm going by. And then when I graph y equals the secant of 2x, my asymptotes are at, it looks like pi over 2 plus, and then it'll be plus pi times n, because nope, pi over 2 plus pi over 2. Is that right? No, that's because I'm wrong to begin with. That isn't at pi over 2. What is it at? It's at, what is that? Pi over 4. Yeah, that's why my adding wasn't working in my head. So the asymptote, the first one is at pi over 4, and then how far do I go to get to the next one? Pi over 2, because this is pi, so it's plus pi over 2 times n. As we kind of find different asymptotes x equals. So then I'll just draw those asymptotes in, and I have lots of them to draw. And then kind of thinking about my graph, I'll put this one in blue, and where it's ones and negative ones are my kind of key points, and then I just get these bowl-y shapes in there. Got it? Okay. Now, that's all the trig functions, and I wanted to review those first. Now we want to talk about damped trigonometric functions, and that's where we take a trig function and we use it with the product of another function. So it might be linear, it might be anything as we go through that. And I think if you were in math analysis, we maybe looked at damped functions like one day or something. And so that's what this is talking about. You can graph a product of two functions using properties of individual functions. For instance, consider the function f of x equals x sine x. So we have two functions, y equals x and y equals the sine of x. And remember that this one oscillates between, or the sine, I shouldn't say this one, the sine of x oscillates between -1 and +1, correct? So that's why they're saying down there a little bit that the absolute value of the sine of x is less than or equal to 1. Does that make sense to you? Because as you graph that sine curve, it goes from -1 to +1. And if you think of absolute value as a distance from 0, that distance from 0 is 1. So it goes either +1 or -1. And so that's how we get that. And that's why they're kind of just reminding you of that. And then if that is the case, then 0 is less than or equal to the absolute value of x times the absolute value of sine of x, which is less than or equal to the absolute value of x. So kind of a lot going on that one as we kind of start to look at it. And so then I'm going to go to this next slide because it kind of continues on with that. And then if we kind of figure out what that means, then we get that the negative absolute value of x is less than or equal to x sine x, which is less than or equal to the absolute value of x. And so you can kind of think about that as, you know, kind of that absolute value thing that is happening, and that it's going to be now bounded by this line y equals x or the line y equals -x. So these two lines are going to be the boundaries of this trig function. And then to find some kind of more things about it, and I think when we looked at it last year in math analysis, we just kind of scrolled it in there. And we're kind of going to do that now, but we want to think just a little bit more deeply about this. And this is kind of going to be when there's a max or a min of kind of that sine function. And if you think about the sine function, I'll just kind of sketch one here. Where do those maxes or mins happen? In a regular period, there's 2 pi, here's 1 pi. So they happen at pi over 2 is a maximum. And then the next one, which is a maximum or a minimum, is 1 pi down the road, so to speak. And so that's why we get that this max or min occurs at intervals of pi over 2 plus n pi. There we go. And that's kind of how this is arrived at. All right, so by looking at that graph and seeing where those maximum and minimums occur. Likewise, when we're looking at when these are zeros, when do the zeros occur? At 0, at pi, at 2 pi, at every interval of pi. So that's when the sine of x is equal to 0 at 0, pi, 2 pi. And so you can think of this as x equals 0 plus n pi. Just to kind of know where those are happening as we go through that. So here's the picture. I am going to show this as the picture of this. And in the function f of x equals x sine x, the factor x is called the dampening factor. So you'll want to know that. The factor x is called that dampening factor. And so to graph this, we can graph the two equations, y equals x, y equals negative x, and they kind of bound that. And then we can kind of graph that sine x that kind of oscillates in between and kind of expands out as we go. Yeah, yep, I know. Yes, if you were in math analysis, you've done a section on this already. So the one I want to look at then before we go is this one. So what's our dampening factor here? E to the negative x is our dampening factor. And I think last year when we looked at these in math analysis, we looked at usually linear things. I don't know if we looked at a quadratic or whatever, but I'm pretty sure we did not look at something of the nature of e to the negative x. So the two functions that we're looking at are y equals e to the negative x and y equals the sine of 3x. And so just kind of thinking along the lines of what's happening here, y equals e to the x, or excuse me, e to the negative x, so that's like 1 over e to the x. So that's like an exponential decay is going to come like that, right? So that's what's happening there. And if we just kind of look at these separate to kind of get in our heads what's happening, this is a plain sine function. What's the period of this? 2 pi over 3. The period is 2 pi over 3. So I'm just going to go by 1/3. There's pi, and 2 pi over 3 is right there. So I'll just plot some points. It's sine middle, and there's the end, and it's at the middle, and then it's at 1 and -1. So those are kind of our two things that we're starting out with. I think it's good to kind of look at that and know what's happening. If you think of that last problem, we graphed y equals x, which I think goes like that to you, right? And we also graphed y equals negative x, which goes like that. So when we are graphing this, the dampening is going to happen by y equals e to the negative x, and what's the other going to be? Which is what? The opposite. Negative e to the negative x. So those will be the two functions that we'll be graphing. And if you just kind of get that in your head, right away I can kind of think about my answer. And before I do the kind of big mathier part of figuring that out, so I'm going to have this, and I'm going to have this. And then my sine function is kind of going to go oscillating somehow in between those two. Do you agree? And, you know, and something like that, right? So now I want to kind of fine tune this just a little bit so that I kind of get a better idea of really what's happening there mathematically, because I want you to understand that. And if I don't have time, I'll finish it tomorrow. Each function has the domain of all real numbers, just as a reminder. And we also know that y equals e to the negative x is always positive. Do you agree with that? Do you agree with that? Okay, so even if I put in negative values here, actually they'll be high. If I put 100 in here, e to the negative 100 is close to 0, but not less than that. So it's always greater than 0. And we also know that that the sign of 3x in absolute value has to be less than or equal to 1, correct? Because it oscillates between positive and negative 1. So that gives us this. E to the negative x times the absolute value of sine 3x is less than or equal to e to the negative x. Does that make sense? Since this bounds between positive and negative 1, then when I'm multiplying times e to the x, that's what it'll be. To remove the absolute value, we say that this will hold, and then also this is greater than or equal to negative e to the negative x. So the way we can write that is negative e to the negative x is less than e to the negative x sine 3x, which is less than or equal to e to the negative x. And we'll kind of look at that at the beginning of the hour tomorrow because I want to kind of take a few minutes to do that.